Hi, and welcome to the Fundamental Theorem of Calculus. My name is Tuesday J. Johnson. I'm a lecturer at the University of Texas El Paso and an assistant professor at Doña Ana Community College. This calculus lecture comes to us from Chapter 4, Integration, in Larson's 11th edition calculus text, Section 4.4, the Fundamental Theorem of Calculus. And this is part 1. I have divided this section up into 3 different lectures. We're going to talk about the first fundamental theorem of calculus, the mean value theorem for integrals, and the third one is the second fundamental theorem of calculus. So here we go. First of all, the fundamental theorem of calculus. That just doesn't look right. Let's put it a little bit better on the screen here. If a function f is continuous on the closed interval from a to b, and capital F is an antiderivative of little f on the interval from a to b, then the integral of f of x dx is equal to the antiderivative at b minus the antiderivative evaluated at a. This is huge. We don't have to worry about circles and squares and triangles and the area formulas of this and that and everything else anymore. We can actually find the area just using the antiderivative. So, when we evaluate the antiderivative from 4 to 9, so I'm going to call that the integral from 4 to 9, it just flows better, of 5 dv. Well, we know that the antiderivative of 5 is 5v, and then we have this line, and it says evaluated from 4 to 9. And remember, in the fundamental theorem of calculus, it was top minus bottom when we evaluate f of b minus f of a. So I'm going to evaluate 5 times 9 minus 5 times 4. Yes, I had to write those in by hand because no, I don't have complete command of my computer yet, but I'm getting there. I'll figure that one out. I know I found it somewhere. 45 minus 20 gives us 25. So the area under the curve, y equals 5, from v equals 4 to v equals 9, well, that's a distance of 5. That's a height of 5. It is a rectangle. It's an area of 25. Absolutely. Yes. So our antiderivative process works with the geometric formulas we saw in the last section. The integral from 2 to 5 of the function negative 3x plus 4 dx. So I'm going to find the antiderivative. So the negative 3 is just a constant. It hangs out. Antiderivative of x is x squared over 2. The antiderivative of 4 is 4x. I'm going to evaluate from 2 to 5, which means I take this expression and I substitute 5 everywhere I see an x. I take this expression and I substitute a 2 everywhere I see x. I'm going to subtract. 5 squared is 25. 25 times the negative 3 is a negative 75 over 2. 4 times 5 is my 20, minus sign. 2 squared is 4. 4 times negative 3 is negative 12. Divided by 2 is negative 6. And 4 times 2 is 8. I do little bits here and there. If I have 8 and negative 6, that's 2. But I'm subtracting 2 from my 20. So negative 7 halves plus 18 turns out to be negative 75 halves plus 36 halves, which is a negative 39 halves. This negative area tells me a lot. How can an area be negative? This tells me that the majority of this graph is below the x-axis. A negative area will indicate below the axis, the majority of the area being below the axis, whereas a positive area, 25, indicates that the majority of the graph is above the axis between the two given values. Number 3, the integral from negative 1 to 1 of t cubed minus 9t dt. That's the integral from negative 1 to 1. The integral of t cubed is t to the 4th over 4 minus 9. Leave our constant alone. Antiderivative of t is t squared over 2. Evaluated from negative 1 to 1. Meaning, first I put a 1 in here. 1 to the 4th is 1. So 1/4 minus 9 halves, right? 1 squared is also 1. But see, the nice thing is this t to the 4th and t squared, those are even powers. So when I evaluate at 1, when I evaluate at negative 1, either way, I'll end up with 1/4 minus 9 halves minus 1/4 minus 9 halves. And whatever this number is, I'm going to subtract that same amount. That's 0. And we're going to find in section 4.5 that that's not a coincidence. It happens to be an odd function. over a symmetric interval, symmetric in the form of 0 is the midpoint of our interval. Turns out the area is 0. We'll have exactly as much of this function above the axis as we do below the axis on this particular interval, so the areas cancel each other out. The integral from -2 to -1 of u minus 1 over u squared. Well, the first thing I'm going to do is I'm going to rewrite 1 over u squared as u to the -2. So the integral of u is u squared over 2, the minus sign. Integral of u to the -2 is u to the -1 over -1. Remembering antiderivatives, we add 1 to our exponent. This is evaluated from -2 to -1. So when I input a -1, -1 squared is 1. -1 to the -1 power, that takes it to the denominator. So I'll have a -1, a subtraction, and then a -1 in here. 3 negatives make up subtraction of 1. Put in -2, so -2 squared is 4. 4 over 2 is 2. Couple of negatives make a positive, but this is a 2 in the denominator and it's a -2, so I have 3 negatives. Makes a -1/2. 1/2 minus a -1/2 makes a 1. -1 minus 2, so I have 1 minus 1 minus 2 gives me an answer of -2. The antiderivative from 0 to 2 of 2 minus x times the square root of x. Remember, the square root of x is x to the 1/2. So what I'm going to do is distribute. I'm going to multiply the square root times the 2, and I'm going to multiply the square root times the x. And that's how I get this new integrand. We don't have a product rule for integrals, and we never will. So when I distribute my square root of x times the 2 and times the x, I do it with rational exponents rather than radical form. The antiderivative of 2x to the 1/2, I have 2. Add 1 to the exponent, that's x to the 3/2, divide by that new exponent, 3/2, minus the integral of x to the 3/2, add 1, that's x to the 5/2 over 5/2, and I'm going to evaluate that from 0 to 2. But this looks horrible to evaluate, so let's clean it up a little bit. Dividing by 3/2 is the same as multiplying by 2/3. 2 times 2/3 is 4/3. 2 is my denominator, is a square root. 3 is my numerator, so I'll have the x cubed under the square root. Dividing by 5/2 is the same as multiplying by 2/5, again a square root, and then x to the 5th, evaluating from 0 to 2. So when I put 2 in, I have 4/3, a square root of 2 cubed, minus 2/5, the square root of 2 to the 5th. And when I insert 0, when I evaluate 0, I get 0. I love zeros. They're nice to work with. The square root of 2 cubed, that will be 2 square root of 2. So I'm going to multiply 2 times 4/3 and get 8/3, square root of 2. 2 to the 5th underneath a radical, I'm going to be able to take out a 4. 4 times 2 is 8/5, and I square root of 2 in the radical still. Actually, square root of 2 is not in the radical, but the 2 is still in the radical. Notice they both have a square root of 2. I'm going to factor that out. Subtract 8/3 minus 8/5. With a common denominator, I find that this will be 16/15 times the square root of 2. Remember, exact answers require you to be able to do a little bit of this algebraic manipulation. In WebAssign, if you're using WebAssign like we do at UTEP, then if you give me a decimal approximation, WebAssign's going to tell you you're wrong. You must be able to use exact values, fractions, radicals, and all of that. Get used to it. The antiderivative from 0 to pi of 2 plus cosine of x. I know the antiderivative of 2 is 2x. The antiderivative of cosine of x is sine of x. Evaluate from 0 to pi. So I put in pi. That's 2 pi plus, well, what's the sine of pi? The sine of pi is 0. So when I evaluate at pi, I'll get 2 pi plus 0. I know that 2 times 0 is 0. The sine of 0 is 0, so I'm just subtracting 0. 2 pi plus 0 minus 0 is 2 pi. The area under the curve, y equals 2 plus cosine of x. Between the values of x equals 0 and x equals pi, that area is 2 pi. Remember, it's area. the antiderivative, or the integral, from 0 to pi over 4 of secant squared theta over tangent squared theta plus 1. First thing we're going to do is simplify this. We don't have a quotient rule, so we can't do that. We haven't learned substitution yet. Substitution works, but it won't be very helpful here. Keep in mind your basic trig identities. Anytime I see a square, any trig function with a square and a 1, I'm going to my Pythagorean identities. And it just so happens that tangent squared of theta plus 1 is equal to secant squared theta. So when I make that substitution, I'm still finding the integral, so I still write all of my notations until I actually do the operation. This is like a big fancy plus sign, really, right? You have to keep adding, add, until you actually add them. I have to keep writing the integral and d theta, d whatever my variable is, until I actually do the process. But secant squared theta over secant squared theta, that's 1. What's the antiderivative of 1? Well, when theta is my variable, it's theta, evaluated from 0 to pi over 4. And that's literally just pi over 4 minus 0, which is an area of pi over 4. The integral from negative pi over 3 to pi over 3 of 4 secant theta tangent theta. I just so happen to know that that 4 is a constant. It comes out in front. And the antiderivative of secant theta tangent theta is secant theta. Because, I could check by going backwards, the derivative of secant of theta is secant theta tangent theta. So I evaluate at my top limit of integration, subtract, evaluate at my bottom limit of integration. The nice thing is that secant is an even function. It turns out that the secant of pi over 3 is the same as the secant of negative pi over 3. These are handy things to know. Both 2, and that's because the cosine of pi over 3 is 1/2. If the cosine of pi over 3 is 1/2, this secant of pi over 3 will be 2, but 8 minus 8 is 0. It turns out this is an odd function as well, and an odd function over a symmetric interval, I'm always going to get an antiderivative of 0. If you could recognize those, it's helpful. It takes away some of this necessary work. You could just write your answer. All right. Find the area of the region bounded by the graphs of the equation. So y equals, can we even get this all on the screen here? There we go. Y equals 5x squared plus 2, x equals 0, x equals 2, and y equals 0. So a quick and dirty sketch here. What I'm looking for is 5x squared plus 2, something like this, from 0 to 2. Maybe I'll even put those in green. From 0 to 2, wherever that hits. And y equals 0, meaning I'm going above the axis. I'm looking for this area here. All of this. Below the function, above y equals 0, between x equals 0 and x equals 2. And this is how we put it into integral form. It's the limits of integration, the left and right endpoints. So the integral from 0 to 2 of 5x squared plus 2 dx is 5x cubed over 3 plus 2x, evaluated from 0 to 2. I don't know why I didn't put that line on the outside of the parentheses, but alright. So we evaluate it 2, that's 5 times 2 cubed over 3 plus 2 times 2, minus, when we evaluate it 0, both terms are 0. 2 cubed is 8, 8 times 5 is 40 over 3, plus 4. Using a common denominator of 3, 4 can be rewritten as 12 thirds. 40 thirds plus 12 thirds is 52 thirds. Do not use mixed numbers. Mixed numbers are for baking and carpentry. We're not doing either one of those right now. So your answer is 52 thirds. It is not a decimal approximation. That's the exact area. Put your calculators away. We didn't need them at any point in here. Let's find the area bounded by below the graph, y equals 1 plus the cube root of x, between x equals 0 and x equals 8, and above the y-axis. So that's the integral from 0 to 8 of 1 plus the cube root of x dx. The antiderivative of 1 is x. The antiderivative of cube root of x, which is x to the 1/3, right? Add 1, so that's x to the 4/3 over 4/3. Evaluated from 0 to 8. I don't like that whole dividing by a fraction, so let's simplify that. That's going to be x plus 3/4, x to the 4/3. This part is incorrect. I should make that in red because I screwed up. 4/3 is my exponent, just like it was here. My fingers just got a little quick there when I was typing. Good thing is that I used it correctly down here. The 3 in the denominator tells me I'm a cube root. Put in 8. 8 plus 3/4 of the cube root of 8 to the 4th. Minus, when I substitute 0, well, 0 is nice, it's just going to give me a 0. Oh, the cube root of 8 is 2. So the cube root of 8 to the 4th will be the same as 2 to the 4th. This is 8 plus 3/4 times 2 to the 4th. 2 to the 4th is 16. 16 divided by 4 is 4. 4 times our 3 makes 12, and 8 plus 12 makes 20. Finding the area. That's finding the that's finding the definite integral. It's finding the area under a curve as the antiderivative, whereas the derivative was the slope of the tangent line. Area, integral, every single time. That's it for part 1. I promise not to stutter so much in part 2, but thanks for listening anyway.